This video is Introduction to VSEPR theory and how that affects shapes of molecules and ions. Now, there's a good bit of learning in this and a good bit of understanding, so it'll require a lot of practice. Right, so we're going to start first of all, just have a look at the specification. This is on page 9. As I said earlier, I am jumping to topic 1.6 because I think this fits in much better in terms of when we talk about lone pairs and bonding pairs and drawing dot and cross diagrams. I think when we've seen the two-dimensional representation of molecules, and then we can apply that to how we decide or how do we describe the 3D representation of molecules and molecular ions. And it's all to do with how the lone pairs and how many lone and bonding pairs there are around the central atom and how they move as far apart as possible to minimize repulsion. Okay, so that's the key thing, that the electrons hang out in pairs, right? They exist in pairs, but the pairs repel each other. Now, I know that doesn't seem to make much sense when they have negative charges, but that's just how it is, right? It's to do with where they are in their orbitals and so on. Okay, so that's the key thing, right? We're going to look at something called valence shell electron pair repulsion theory, which is basically saying that the electron pairs in the outermost shell repel each other. That's all that is. But this will, because of the way that the electron pairs repel each other, and you have a three-dimensional, if you can imagine you have a sphere, so the way that the electrons repel each other has to be considered in 3 dimensions, not just 2. It's not just flat on a page. You have to think about that. So that'll affect the bond angles. So you need to know, identify the shapes and bond angles, right? And it says just dealing with only up to 6 outer pairs of electrons. And they've listed the shapes. They've just said including, but we'll cover a few more shapes as well. Okay, so let's begin this by having a look at a video by somebody who's got some 3-dimensional representations and a much posher voice than me. So we're going to have a look at that first. Okay.
Let's begin. Have you seen a balloon bender at his art? He blows up a few balloons, ties them together, gives a twist here and a twist there, and a beautiful shape emerges. Similarly, nature's building blocks, the atoms, combine chemically in a variety of permutations to form molecules with diverse shapes. The 3-dimensional arrangement of atoms in a molecule is referred to as its molecular geometry. Many properties of a substance can be attributed to its molecular geometry. Can the molecular geometry of a molecule be predicted? Yes, the molecular geometry of a molecule can be predicted with the help of the valence shell electron pair repulsion theory, or VSEPR theory. What is valence shell electron pair repulsion theory? How does it help to predict the shapes of the molecules? Come, let's learn about the VSEPR theory.
Okay, so just to mention here, right, that, where did I write it down? The VSEPR, so you're dealing with the why, right? The why does VSEPR exist? And that's about the electron pairs repelling each other to minimize repulsion, or to moving as far apart as possible to minimize repulsion. What moves as far apart? The electron pairs. And now you're going to identify the types of electron pairs, or the numbers of electron pairs around any central atom, and then you're going to explain the effect on the shape. Okay?
In this module, what you will learn. At the end of this module, you will be able to describe the concept of the valence shell electron pair repulsion theory, apply the VSEPR theory to predict the shapes of molecules. VSEPR theory, predicting the shapes of molecules. Electrons are the negatively charged particles of an atom. Electrons that can take part in chemical bonding are known as valence electrons. These are found in valence shells, which are the outermost shells of atoms. A chemical bond involves either the transfer or sharing of valence electrons between atoms. The sharing of valence electrons between atoms in a molecule can be represented by Lewis dot structures. A Lewis structure or Lewis dot diagram is a type of shorthand notation which depicts the distribution of valence electrons in molecules. It shows the number of valence electron pairs in each individual atom, including the bonding electron pairs and the non-bonding electron pairs, also known as lone pairs, that may exist in the molecule. Sharing of electrons between atoms gives rise to covalent compounds. Molecules of covalent compounds come in many shapes and sizes. The shape of a molecule can be predicted using the valence shell electron pair repulsion VSEPR theory. The VSEPR theory assumes that the...
Now, I just want you to look at this diagram because actually you have drawn all of these molecules. And if you look at the sulfur hexafluoride as it moves around, you can see because there are 6 electron pairs in the central sulfur atom, they're actually in 3 dimensions as far apart as possible from each other. Same as ammonia, even though there are only 3 bonds here, you've actually got a lone pair of electrons on the nitrogen as well. So it's actually 4 electron pairs. So that means that this shape isn't just flat, right? It means that these are down kind of here, it's trigonal pyramid, because that 4th electron pair, the lone pair up here, also has to be as far apart as possible from the rest. Same with water, it's only got 2 bonds, right? But it's not in a straight line because you have 2 lone pairs of electrons in the oxygen that also have to be accounted for in terms of the shape. And methane has got 4 bonding pairs of electrons, so they're all as far apart as possible. Same in phosphorus pentachloride, 5 electron pairs as far apart as possible. And carbon dioxide has got effectively 2 bonding pairs. Now, I know they're double bonds, but I think I tried to mention earlier that even though they're double or triple, if they're just between 2 atoms, they're counted as 1 bonding pair for this idea of shape. So it effectively has 2 bonding pairs and nothing else. The oxygen's atoms are as far apart as possible.
The arrangement of valence electron pairs around the central atom in a molecule determines its molecular geometry, that is, the molecular shape. How do we use the valence shell electron pair repulsion theory to predict the shape of molecules? To understand this, let us first consider the assumptions made by the VSEPR theory. 1. Valence electron pairs in an atom repel each other. 2. Valence shell electron pairs, therefore, arrange themselves around the central atom in such a way that there is minimum repulsion between them.
Folks, could you look at page 10 of your notes where it's talking about valence shell electron pair repulsion? So you'll see the bullet points on page 10 is really going through now slightly different language to what this person's using, but it's saying the same thing. The first point being that electron pairs repel each other and will move as far apart as possible.
Happens when they are as far apart as possible. For example, if there are 2 electron pairs or electron groups, then these adopt a configuration where the electron pairs are at an angle of 180 degrees, as in beryllium hydride and carbon dioxide. 3. It is this definite arrangement of electron pairs that gives the molecule its distinct shape and geometry. In other words, molecular geometry depends on the electron pair geometry. 4.
Just be aware that those, sometimes they show the lone pairs, normally they're just written here, but sometimes they show them as if they're in an orbital. Now, they're kind of representing them as, looks like a bit of a p orbital. Do not worry about that. That's just how they try to represent where the lone pairs of electrons are, to show that they're sort of taking up space.
A non-bonding electron pair or lone pair exerts greater repulsion than a bonded pair. So, lone pair repulsion is greater than lone pair bonded pair repulsion, which is greater than bonded pair repulsion.
Now, yes, we will get to this, but for molecules, that difference in repulsion actually isn't that significant. You'll see it on page 10 anyway. At the moment, what we're going to focus on is the number of electron pairs and what shape that will give a molecule or molecular ion.
5. For the purpose of determining electron geometry, 2 pairs of electrons of a double bond and 3 pairs of a triple bond are treated as one pair. Let's take a look at the possible geometrical shapes that arise when there are different numbers of bonding and non-bonding pairs of electrons surrounding an atom. When there are 2 electron pairs, the possible molecular...
Now, folks, in your notes, this is started on page 11. Now, it is a lot of information, and there's no way you're going to remember all the shapes, right? But you will need to learn them, okay? You will need to learn the ones that are listed on page 11 and 12. So just flick through and see, just follow what he's doing with your notes.
Molecular geometry is linear. When there are 3 electron pairs, the possible molecular geometries are trigonal, planar, or bent. When there are 4 electron pairs, the possible molecular geometries are tetrahedral, trigonal pyramidal, or bent. When there are 5 electron pairs, the possible molecular geometries are trigonal, bipyramidal, seesaw, T-shaped, or linear. When there are 6 electron pairs, the possible molecular geometries are octahedral, square pyramidal, or square planar. Shown here is a chart which depicts the possible VSEPR molecular geometries. Take a look at it again. VSEPR strategy. Let us now use the VSEPR strategy to predict the shape of a water molecule. First, draw the Lewis structure of the water molecule. Count the total number of electron pairs around the central atom oxygen in the molecule. Determine the number of bonding electron pairs and non-bonding electron pairs or lone pairs. A water molecule has 2 bonding and 2 non-bonding electron pairs surrounding the central atom, making a total of 4 electron pairs. The most stable spatial arrangement of the valence electrons is one in which the mutual repulsions are minimum. Remember that if there are 4 electron pairs around the central atom, the electron pairs experience least repulsion when the arrangement is tetrahedral. So, arrange the 4 electron pairs around the oxygen atom in a tetrahedral configuration. However, this is not the final structure, as the electron pairs are not similar. The effect of the lone pairs has to be brought into the picture. The presence of the lone pairs distorts the shape. The lone pairs exert greater repulsion on the bonded pairs, resulting in the bonded pairs being pushed closer to each other. Next, determine the molecular geometry. To do this, only the atoms need to be considered. So, ignore the lone pairs and look only at the arrangement of the atoms. We observe that the atoms are arranged in a bent or V shape. Alternatively, once the numbers of bonded and lone pairs have been determined for the Lewis structure, the shape is identified using the VSEPR molecular geometry table.
Okay, so that's the end of that video. I shall put it, oops, I don't want to do that. Okay, I shall put it on the shared, the Google Classroom anyway. Okay, so where are we at? If you turn to page, we're just going to do a couple of these and then I'll end the video and let you do the rest yourselves. Right, so if you turn to page 10, 11 actually, some of the headings are on page 10 and then I have to move over to page 11. So have a look. Okay, so you're going to count the bonding pairs and lone pairs, right? So we're going to have a look at some of the molecules you've used already. So what I want you to do is turn to page 1 and have a look at some of the molecules you've already drawn, right? Now, I should say that something that's just diatomic is not going to have a bond angle. You need to, now they have asked this in some past paper questions, but it makes no sense. A bond angle is like an angle in a, anything in a triangle. You need two different lines. You need you need to be able to measure a bond angle between two different lines, right? If there's only one bond, then effectively there is no bond angle because there's only one bond. But you can do it for water. So have a look at water here, and first thing to do is identify the number of electron pairs. If you look at water, okay, and it's H. Okay, so electron pairs. And then you look at lone pairs, number of bonding pairs. Right, so for water, you've got 4 electron pairs, you've got 2 lone pairs and 2 bonding pairs. Now if you turn to your diagram table on page 1011, okay, so what you want to do here is have a look. So first thing we want is number of electron pairs. We want to go down to that, so it's 4, right, and then we want to find the match up between, so this one here is for 4 bonding pairs, no lone pairs, 3 bonding pairs, 1 lone pair. Turn over the page. Going to get to 2 bonding pairs, 2 lone pairs. Okay, so that matches up. So what we want to put in this last box here is examples of molecules that have that shape. So that means that the water molecule in 3 dimensions has a bent or V shape, sometimes called V shape. Bent is what they have in the specification, but V shape is okay as well. Right, let's have a look at another one. Right, page 3, right, there's methane. So have a look, and I had actually tried to get you to assign the different numbers of electron pairs to get you in the kind of habit of that. Right, so let's try methane. Okay, so methane has 4 electron pairs as well. This time though, it has no lone pairs and it has 4 bonding pairs. So we need to find that matchup. On page 11 and 12. So we're still at the 4 electron pairs. Right, so down 5, 4 electron pairs, and we have 4 lone pairs. Sorry, 4 bonding pairs, no lone pairs. So the shape is going to be tetrahedral. So we're going to write in there CH4, e.g. methane, CH4. So methane has that shape. Okay, so what I want you to do, and I shall deal with it in the next video, is I want you to try it for, let's see. If you look at the molecules that you drew on page 7, right, try and assign those. Now, as I say, ignore the diatomic molecules, but I want you to do it for ammonia, the ammonium ion, the aluminium tetrachloride ion. Don't worry about that. Yes, this one, and this one. So I want you to do all except the diatomic molecules. See how many of those you can assign, and I'll work through that in the next video. Okay, so just get the molecules and molecular ions on page 7 and see if you can add them to the table on page 10, right? So see, unfortunately, right, the examples are in the far right column. So I just want you to see if you can assign each of the molecules based on the number of electron pairs, number of lone and bonding pairs in the central atom, where they might go. Okay, and I'll cover that, the answers to that in the next video.